Okay guys, this is Madhav PVL and today we are going to discuss about heap sort. So basically we had just discussed about this binary sort and we also discussed about shell sorting. Now we are going to discuss about heap sort. So heap sort is a basic application for binary search tree. So it is one of its application. So let me just show you the basic definition. So heap sort is a comparison based sorting technique based on binary heap data structure. It is similar to selection sort where we find the minimum element and place the minimum element at the beginning. So in insertion sort, we will just compare one element and we will just place it in a order which is in ascending order. But we in heap sort we are going to just delete each element from backward to front. So with the help of binary search tree, we will just confirm this heap sort. So let me just show you anything. So heap sort is completely based on binary search tree. So now I am going to just sort these elements 7, 9, 30. Yeah. Now these are the elements which I'm going to sort now. So basically, before we need to just sort these elements, we need to just know a very basic rule. So basically, if we need to just sort the elements in a heap sort, so its binary tree must be a complete binary tree. So what is meant by complete binary tree? So let's just see its basic definition. Complete binary tree or full binary tree. So it is a tree in which every node other than the leaves has two children. A complete binary tree is a binary tree in which every level except possibly the last is completely filled and all the nodes are as far as left as possible. So these are the conditions which we need to satisfy to just form a complete binary tree. So let me just start this. So now we need to just insert an element that is 15. Now for 15, I am just creating a node. So after creating 15, so we need to just as our basic rule for complete binary tree. So let me just note it down here. So this is one of the important point which we need to just remember. Complete binary tree. So in complete binary tree, we need to just remember one thing. So basically, if we need to just insert any element into a complete binary tree, first we need to just occupy its left position, then we need to check its right. Otherwise, complete binary tree doesn't form a proper tree because every node at its base position should have equal number of nodes. That is possible only if we just perform this left side thing. So if we just can remember this thing, so we need to just first insert the elements to its left side, then we need to just check about the other thing. So okay, now not the complete left side, so let me just show you one node. So now I am going to insert 20. So 20 I am going to insert towards left. You may just get it out like as 20 is bigger element, how can we just insert to its left? So let me just go in detail. So if we just insert this into 20, so now we need to just insert 7. So before inserting 7, we can just come to a conclusion like as root node is lesser than that of the child node. So it is not at all possible in a binary tree condition. So now we need to just swap the elements. This is okay, but we shouldn't just occupy the right space first. So that is the basic rule, golden rule. So yeah, now 20 and then it's 15. So now 15 should be to its left. And now we need to just insert 7. So 7 will be towards its right as we need to just occupy this space. So now I am just making it to its right node. So it's not a complete binary tree, but we need to just satisfy some of its conditions. So then next 9. So 9 should be placed at its 15th as it is less than 15. So it needs to be placed at its left position. Yeah, now it's 9 and then 30, which is to be placed at its right position. 30. So now I'm just making it a node, and then we need to just join like this. So 30 is towards its right. So like this, we are just making a node. So now we need to just check like as root is lesser than that of this thing. So we can just swap the elements. So we need to just swap this 30 with 15 and then 15 with 30. So after swapping, we can just write like this 20 and then 15 and then 7 and then to this 9 and sorry, I had just made a mistake. So here it is 30 as we are swapping, and here it is 7 and then here it is 9 and then here it is 15. So in this way we need to just swap the elements. So in this way, we need to just swap the elements. So now I'm making these things. As now we can just see here it is satisfying the whole condition. As we can just say like root node is just greater than the child node. So basically, but it is not satisfying here if we can just see as root is lesser than that of the child node. So we need to just swap it here to make it a complete binary tree. And then it becomes like this 30 and then here it is 20 and then here it is 7 and then here is same, so here it is 9 and then 15. So now let's just make it like a tree. So the basic condition is the root node shouldn't be less than that of the child node, so that rule must be remembered. So it's to its left and to its right. So we need to just write its pre-order position, that is so we need to just maintain a level like root left right, root left right. So we need to just maintain a level like that. So we need to just write it in an upside down order. So now I am writing like this 30, 20, 7, 9, 15. Yeah, now in this way I am just making it like an array. So I am just making this tree as an array. So I'm now making this as an array. So now we need to just delete one of its element and then we need to just make its last position as its first position. So let me just explain this with the help of this tree. So from now onwards, I think we need to just put some extra concentration, guys. So basically here the largest value is 30, right? So here the largest value is 30. But according to the array, it is in its first position. So now we need to just maintain another array in which we can just delete the elements. Like, so now I'm going to just delete this 30 element. So after deleting 30 element, I am going to just enter it in this array. I'm just going to enter it in this array. And then now the tree becomes like this. So it's an empty node because 30 is deleted. And then it's 20 and it's 7, 30. So sorry, 30 is deleted. it's 20, and then next is 7. So now the remaining elements will be like this, same. So 9 and then 15. So 9 and then 15 are same. Now one of its node is empty. So we need to just remember one thing. So if we are just going to delete one of its top element, then we need to just occupy its space with the help of its alternative element. That is, don't think so much. So 30 is alternate is 15, right? According to its present state. So according to its present position. So 30 is alternate element is 15. So now we can just write that 15 there. So we can just remove this 15, and then we can just write it over there in its empty position to just occupy its root position. So now I am writing the 15 here. So after writing 15, so again we need to just check some binary conditions. Like here we can just see the root node is smaller than that of the child node. That is, we need to just make a swap here. So after making swap, so the elements will become like this. So that is, the root node will become 20, and then its left position will be 15, and then this is 7, and then this is 9. So I think now everything will be satisfying right there, right here. 20 and then 7 and then 15 and then 9. Finally the 9. So now with the help of making it like a tree. So now I think till here it's clear, right? So now we may just get a confusion like here the array value is different. So its array position is like this. But for this tree, the array position will change, like, right? So we need to just write another array list. So we need to just write another array list like this. So now I am writing another array list, that is so now we are having 20 at its top, and then 15, and then 7, and then 9. So this is its present array position. So now let me just keep it as an array. So this is at tree 1, and this is at tree 2. So now we need to just delete this 20, and then we need to just replace it with the help of its base value. So now I am going to just delete this 20 here. And then after deleting 20, and I'm going to just place this 9 value here. So after deleting 20, our node will be like this. So now I'm going to just draw the tree. So now this position will be empty, guys. So this will be 15, and this will be 7, and this will be 9. So this will be its position. These are the positions at present. That is tree 3. So now we need to just replace the value of 20 with 9, which is its base value. As we can just see here, this is the present array list position. So now I will just delete this node right here. So now I will just write here, that is 9, and I'm going to just replace this with 9. So now I'm going to just delete this array position here, and then I'm going to just write it there. And then we are remaining with 15, 7, and 9, and the order will be changing. So now tree 3 will be in this position. So now I'm going to write this 9. Sorry, so I had just forgotten to just perform a very basic rule, that is we need to just swap these elements, right? because the child node is larger than that of the root node in this case. So now 15 should reach to its top position. So now I am writing 15 here, and then 9 will be here, and then 7 will be here in this position. Yeah, now so I'm just going to write it. So with the help of this, I'm just making it like a tree. So with this, so now we need to just we need to just draw another tree that is 15 as head is containing 15 and then 9 and 7. So we need to just maintain it in the form of an array that is like this. So this is tree 3. So now after this, we need to just delete this 15 element and we need to just replace it with 7 as 7 is having last. So we need to just remember a very basic thing. So 30 will be replaced with its last position, that is 15, and the 20 will be replaced with the help of its last position 9, and now 15 will be replaced with the help of its last position, that is 7. So now I'm making another tree for this alternative. So I am just going to delete this element and I'm going to just insert this in its position. So now this will be empty, guys. So 15 will be empty. Let's make it some large. So 15 will be empty, and then this is 9 and this is 7. So 9 and 7 positions are same. So 9 and then 7. So I'm using the brush and joining it. So this position will be empty and I'm going to just use this 7 value to replace it. And I'm going to just delete this element. And then we are going to just place the 7 value here. As I had just deleted the 15, so now I'm going to enter the 15 value here. So 15 value is entered here and we are just remaining with the elements 9 and 7. So basically now we need to just perform another basic binary operation, that is, as child node is greater than that of the root node, we need to just swap the elements. There is no such a rule like this condition may occur in each step, but according to our example, we are just facing this condition many times. So it depends upon the values which we are going to just use this heap sort, in which we are going to just use this heap sort. So yeah, now I'm going to just write the 9 value here and then 7 here. So with the help of this expression, I'm going to just maintain a relation with this. And now I think this tree value is NF. So, so actually we need to just maintain it like a tree 4. Yeah, now it's tree 4. So yeah, now we need to just replace the value of 9 with the help of 7, and then 9 will be deleted first. So after that 7. So basically, so finally the elements is sorted. So this is the sorted order. So in this way, we can just perform a heap sorting. So this is the very basic sorting for the heap sorting. Thank you for watching.